Good afternoon, everyone. Thanks, Xingyu, for the introduction. This is Yuan Chao Shu from Microsoft Research Asia. I'm very glad to be here to present our recent work titled Last Mile Navigation Using Smartphones. This is a joint work between Zhejiang University, University of Michigan, and University of Minnesota. So navigation, in a broader sense, refers to any skills or studies that involves the determination of location and direction. So in any form of transportation, navigation becomes inseparable. And our ancestors have devoted a large amount of efforts in designing different kinds of navigation instruments. Before going to the design of our system, let's take a look at the working principle of modern navigation system. So as a first step in a navigation system, we need to do positioning. That means we need to know where we are and where we are going. And then we need to pinpoint the starting position and the end position in a map and use some path planning algorithms to plan a route from the starting point to the final destination. So thanks to the development of the satellite-based positioning system, so meter-level positioning accuracy could be achieved in outdoor environments using this GPS or GLONASS or Beidou in China. And recently, a lot of research work has been proposed to localize both devices and users in indoor environments. And for path planning, it's a well-studied topic in both robotics and mathematics. However, it's another story for mapping. Although there exists a lot of methods to get a map, such as satellite mapping, wall driving, and floor plan mapping, all of them has their disadvantages. So actually, the lack of map information becomes the bottleneck of current navigation systems. So this could be explained from the following three aspects. The first one is coverage, second one is resolution, and the third one is fidelity. So it is obvious that there is no map that can cover every single corner on the Earth. And also due to the existence of these provisional passes, the map may become invalid after a certain period of time. For example, in typical Michigan winter, these trails or even these trunk roads will be covered by the heavy snow. So note that all three components, the positioning, map, and path planning, are important in the navigation. And the navigation is weaker or even fails when one of the three cannot be performed at a given location. So actually we find that navigate one to the vicinity of the destination tens of miles away could be achieved using legacy navigation systems such as Google Maps. However, they may fail to find a feasible path from there to the final destination. So we term it as a last mile navigation problem. So to deal with this problem, in this work, we propose a plug-and-play, lightweight, smartphone-based last mile navigation system called Follow Me. So the basic idea of Follow Me is to explore the sense left behind by previous travelers. And in general, there are two phases in Follow Me. The first one is leader's trace collection phase, and the second one is the follower's navigation phase. So in leader's trace collection phase, the smartphone will do the following three tasks. The first one is to record a bunch of sensory data with the smartphone during leader's walking trip. So in the current implementation of Follow Me, we use this geomagnetic field to do this trace synchronization. And the second thing is, during the user walking, the system will also record sporadic walking patterns like making turns or go upstairs of the user. And then all this sensor information and this detection result will be combined together to build a reference trace. And in the follower's navigation phase, this reference trace will be passed to some followers, and then during his walking, the synchronization algorithm will synchronize the online sensory observation with this reference trace and notify the user to take actions when he, for example, approaching the staircase or approaching this crossing. So this video shows how it works during the navigation phase. Look at the icon on the smartphone screen. If it becomes, let's say, left, it means that the user needs to make a left turn in the next crossing. And when the user finishes crossing, it becomes up. That means you just need to go straight. So follow me can be used in different scenarios. Here we only showcase a few examples. The first one is office environment. For example, the meeting coordinator, they can provide these traces from the entrance of the building to the conference room to the meeting attendees to help them find the meeting venue more easily. And also, very big shopping mall, vendors and the restaurant owners can collect the data on their own from several entrances of the mall to their shop and share it on the cloud for promotional purposes. And also it could be used to find these AEDs or emergency exits, and also you can use it to find your car in a large parking structure in the airport after a multi-day trip. Now let's go to take a look at the detailed design of Follow Me. So in the trace collection module, it uses the sensory data collected by different kinds of sensors, including magnetometers, accelerometers, gyroscope, and a barometer. So different sensors have different purposes. So for example, the magnetometers are used to collect this, to sense this indoor or semi-indoor geomagnetic field and used for later synchronization. And the accelerometer is used mainly for step detection. And when combined with the gyroscope, it could be used to detect the turns. And the barometer is used for level change detection. Note that different combinations of sensors could be also used to achieve the same goal. For example, the accelerometer could be also used to help detect this level change. And all this data, all this information are packed together to generate this reference trace. Let's take a closer look at the structure of the reference trace. So basically, the reference trace consists of two kinds of information. The first one is sensory data, and the second one is detection results. And all this information are timestamped. So in the time domain, we can view these different kinds of data as information that's sampled at different frequencies. And then we merge them to the time frame to build this reference trace. Then in the navigation module, the most crucial component is a working progress estimator. So it took the reference trace as well as this magnetometer observations and accelerometer observations as inputs and detect that and synchronize these two traces to generate these navigation instructions. And another component is a deviation detector. It will detect if the user or the follower goes off the trail. If that happens, it will notify the user to go back and until he arrived at the correct trace and continue to the final destination. So all these are achieved through these navigation instructions shown on the smartphone screen, as shown in previous slides, which is the blue icon on the smartphone screen. So due to the time limit in this presentation, I'll mainly focus on the design of this working progress estimator. So in the previous slide, we know that the trace synchronization is the most crucial function in this working progress estimator. So now let's take a closer look at how it works. So the left two figures shows our two floor maps in an office building, so actually the X building in the University of Michigan. And the upper one is the third floor and the lower one is the fourth floor. So we can see that there's an entrance on the third floor. And suppose that there's a meeting which will be held on the conference room 4941 on the fourth floor. And the meeting coordinator enter into the building from the third floor, and he firstly go upstairs and make several left turns and finally arrive at the conference room. During his walk, follow me records the geomagnetic traces, which is shown in the right figure. In addition to that geomagnetic field, it also recognizes these user walking patterns, like when the leader is at position A, he go upstairs, and at position B, C, D, he made left turns, and the leader arrived at the destination at E. So then the right figure, which is the reference trace, is passed to the follower, and the meeting attendees arrived at the entrance of the building and started walking. So once the follower arrived at the entrance and walked for 10 seconds, follow me detect that he is at the location capital A through the trace comparison. Therefore, an instruction of go upstairs will show on the screen. During the staircase climbing, follow me continues collecting the geomagnetic observations. When it finds that the user approached the end of the staircase, it will notify him to make a left turn. This way, follow me is able to provide navigation instructions and guide the follower to the conference room in an online manner. So in that example, we can see that the geomagnetic measurements comparison and the trace synchronization plays an important role during the navigation process. So in Follow Me, we designed a step-constraint trace synchronization algorithm based on the dynamic time warping. So dynamic time warping is an algorithm for measuring the similarity, commonly the Euclidean distance, between two temporal sequences, which could vary in time or speed. It calculates the optimal match between them using dynamic programming. So let's use an example to illustrate how DTW works. So given a reference trace and a user trace with 7 samples, DTW first creates matrix 7 by 7 warping matrix, which stores the similarity of pairs of samples from both traces. The value of each grid in the matrix is updated iteratively following the equation below. Given that the first user observation, DTW updated the bottom row in the matrix, once the entire matrix is updated, the algorithm will trace back from the end to the beginning to find the optimal matching, which is looked like in the right figure. So in that example, we find that in Lab-C dynamic time warping, the algorithm needs to have the full knowledge of both traces. However, in our Follow Me design, the system continues to collect this observation of geomagnetic field during user walking. In addition, the Lab-C dynamic time warping algorithm incurs a quadratic computational complexity, which is unacceptable for smartphone applications. To deal with this problem, we designed online dynamic time warping with linear computational overhead. So the main novelty behind that is we use a step to constrain the search space in the warping matrix. So let's still use these two traces, which has 7 samples. And the number here refers to the step numbers. So for simplicity, we assume that there's only one sample took in each step. So at the beginning of the dynamic time warping algorithm, the first sample in the user trace maps to the first sample in the reference trace. And the third sample in the user trace could map to the first one, or the second one, or the third one, or even the fourth one in the reference trace. However, it is very unlikely that the second sample in the user trace maps to the 7th sample, for example, in the reference trace. Why is that? It is because if the second sample maps to the seventh sample in the reference trace, it means the physical distance covered by one step of the follower takes 7 steps of the leader, which is unlikely to happen in reality. So in our proposed online algorithm, we set a DTW buffer size and a pointer to indicate the direction of growth of the matrix. In this example, the buffer size is set to 3. Therefore, we first calculate the 3 by 3 matrix, and the pointer is at 3, 3, 3. The algorithm then looks for the local minimum value in the matrix, say the 3, 3, 2. Therefore, the point moves towards the upper direction of the matrix and can update the values of the 3 grids in that row. If the local minimum grid located at the corner of the current matrix, the pointer moves towards both right and up direction. The process continues until we reach the end of the reference trace. So the warping matrix in 3D space is shown here. So since the proposed online dynamic time warping dynamically changed the search band, so we get rid of the unnecessary computation of values of grid which are far away from the optimal path. So we have fully implemented Follow Me on Android-based smartphone. 2 threads are used, with the first one collecting sensor data and the second one taking care of this signal processing in asynchronously. So firstly, we will show the CDF of spatial error in navigation. The spatial error is calculated as the distance between actual turn points of the follower and the estimated location provided by the online dynamic time warping algorithm. It indicates the trace synchronization performance using geomagnetic observations. And we also compare the performance of Follow Me with 2 particle filtering based navigation system using both geomagnetic field and Wi-Fi ISSI signal. So in that figure, we can see that the Follow Me system achieves a comparable result with these 2 benchmarks. However, we get rid of this labor-intensive fingerprint view process. We also show this lead time of navigation instruction at different checkpoints. So the lead time indicates that how early our system will notify the user to take actions before they arrive at some crossing or staircase. So we find that follow-up offers a 5 seconds lead time on average, which is sufficient for the user to take actions. So before concluding my presentation, I want to briefly mention some related work to this work. So localization and navigation has been extensively studied in the area of robotics. However, the human locomotion is way more complicated compared with these robots. And also the limited sensing capability and the computation capabilities on smartphone brings a lot of difficulties in both localization and navigation. And smartphone-based navigation and localization could be broadly categorized into 2 categories. The first one is infrastructure-free, and the second one is infrastructure-dependent methods. So both of these 2 kinds of methods have their advantages and disadvantages. So in Follow Me, we borrow some ideas from these methods, like we use some IMU-based method to detect this user working patterns like turns and go upstairs. However, we get rid of this fingerprint map construction process. And also, geomagnetic field has been proved to be stable in indoor and semi-outdoor environments and has been used to help localize devices. And however, they either use this customized hardware or they still need to build a fingerprint map before running the system. And recently, there's also a few leader-follower based systems proposed in our community. And however, some of them use customized devices like robots, and some of them need this rely on the infrastructure. For example, they're using Wi-Fi, or they need this pre-deployed Bluetooth speakers. And some of them impose some constraints on users. For example, they leverage the intelligence of users to compare some images. In summary, Follow Me is an infrastructure-free system which could be either cloud-based or ad hoc. And we do not need any information about the floor plan, and we get rid of this Wi-Fi and Bluetooth deployment. And it's a high-efficient navigation system which uses low-power sensors and has low computational overhead. And also, we try to minimize the user involvement during the navigation process. What the user needs to do is only look at the navigation instructions on the smartphone screen, which makes the system plug and play and with fast and easy bootstrapping. So this is a short demo of the, how Follow Me works in a multi-level indoor environments. So the user launched the system and load the reference trace. And so the trace starts from the room 3965 to 4645. And he pressed start after loading the trace. And just what all the user need to do is look at the icon on the screen. So he just now he need to turn left on the next crossing. And yeah, when he finishes this turn, the arrow becomes up, and he just need to go straight. And now it means the user need to turn right and go upstairs. Okay, so he find the staircase and go upstairs. Yeah, I think I'm run out of time, so. When the user is approaching the destination, and stop icon will show, and we find that, okay, yeah, he arrived at the room 4645. Okay, thank you for your listening, and for more information and updates, please follow me.
Thank you.
I'm glad to take any questions.
Thank you.